Hello everyone, and welcome to Unlocking the Secrets of Complex Pesticide Residues, Advanced Techniques with Compound Discoverer Software. I'm Matt Thorne of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Thermo Fisher Scientific. To learn more about our sponsor, please visit thermofisher.com. We do encourage you today to participate by submitting any questions you may have during the presentation. To do so, you can simply type those into the Ask a Question box and click Submit. We'll answer as many questions as we have time for at the end of the presentation. You can also use that to submit any technical issues there if you're having any trouble seeing or hearing the presentation. I'd now like to welcome our speakers, Ralf Tautenhahn, Product Manager at Thermo Fisher Scientific, and Julio César Espana, Postdoctoral Researcher, National Food Institute at the Danish Technical University. For a complete biography on our speakers, you can click on the biography window on the left side of your screen. Julio, you can go ahead and begin your presentation.
Thank you for the nice presentation. Today, we were going to dive into the analysis of pesticide residues, and we will take a look into other molecules present in protection products. This is a subject that's also relevant for food safety. By the end of the session, we will walk away with some useful information from the research group in analytical food chemistry at DTU. I would like to start taking you to the presentation contents, to multi-residue analysis. Then we will move on to explore other contents of the plant protection products, their characterization, and then we will need to face some challenges during the sample prep. Next, we will assess the method performance to finally conclude some key points on the study. At the moment, we've seen a progressive shift towards a non-target scope, not only to detect pesticide residues, but also to identify contaminants at the same time. General and often desirable requirements include high identification rates, easily coexisting with quantitation, and ensuring that missing values are minimal. Different screening workflows like data-dependent and data-independent acquisition have been explored to assess their performance, along with their limitations. And what has been found is that DAA excels identification rates in demanding application. So we decided to put in test our method for small molecules, focusing on the confirmation of pesticides, and DAA clearly reached a higher coverage and is not that affected by the concentration as DDA did. Here we see also that DDA have different flavors, schedule, and the Aquarius deep scan that showed a higher confirmation rate, but below the DAA acquisition. I think I'm not alone in feeling that the DAA could completely take over DDA in the future, as new algorithms efficiently assist making narrower DAA windows as possible without impacting neither the cycle time nor the accuracy of precursors or products. In DIA, segments of ions are sequentially fragmented while the separation takes place. This can be multiplexed for improved efficiency. Then, the data could be fed into the compound discovery workflows in order to analyze and review data. Automated spectral lab research makes use of MSET Cloud, which shows the spectra and compares it to the reference and auto process libraries. The difference impacts the scores, but we need to keep in mind that the confidence of the acetamiprid hit relies heavily on the context, like the collision energy from the library, which is, in our case, multiplexed. A couple of things I'd like to point out regarding the complex residue definitions. First, they rely not only on the parent compound, but on other residues, and all must be taken into account to assess the consolidated LOQ that must be at least at the MRL to be a fit for purpose method, let's say. However, it's worth to mention that is not applicable to all commodities, since the N-desmethyl acetamiprid is only required for animal origin and honey. But we have here the to the hits, we can see that the spectral quality is impacted. Foreign components into the isolation window lower down the scores. The also known chimerism, which in some cases, like here for imidacloprid, could represent a huge difference for the library hit. So low scores obtained are potentially connected to several causes that would require verification. So following the Sante identification criteria that calls for the extracted peaks that fully overlap, you can get either an ideal clean DDA spectra to a DIA with higher identification rates at the expense of complex chimerism. We then made an evaluation over more than 100 diverse food samples with findings but also false negatives in the inner ring. For example, bixafen accounts for almost 25%. The bar plot shows the false negatives and true positives per matrix, but there is a caveat. False rates highly rely on the sensitivity on the fragments for the confirmation below 10 ppbs, which are easily achieved by triple quad technology, here with risk of false positives, false negative results, which still must be handled with caution, especially for low concentrations that make up these complex emeralds definitions. Now, in addition to the active ingredient in the plant protection product, there is a lot of compounds that can be behind. But first, we will need to revisit a basic concept. The European Chemical Agency classifies substances into compounds with less than 20% of impurities, or by several constituents, like mixtures. However, these are some substances that are made of complex mixtures of unknown composition. That is the case of these linear ethoxylated alcohols, which, despite having a signed Cas number, no molecular formula is still defined. Recently, these coformulants are regulated by applying similar criteria to pesticides. Some small molecules have been studied ever since, and also large alcohols with defined molecular masses. So we need to understand the analytical target, starting with the full scan acquisition. We found a particular pattern from the mass spectra. These delta units revealed a multiple charge clusters from the isotopic profile, described in the family of compounds where the fragmentation is not specific, leading to rely solely on the accurate mass only. Now on. However, we struggle with the matrix match calibrations in white squares. This background might come from the matrix itself, so we move forward to break down the sample prep. We started to investigate the steps involved in the Ketcher's method. So we did several comparisons with a reagent plant and a glass Pasteur pipette in each step. The different steps show differences against the reference, but it's difficult to tell among these steps. So, taking into account that repeating units are characteristic features of these families, we made use of the Kendrick mass defect expression to normalize the mass of the common repeating unit, and then the mass defect. Depending on the rounding, we obtain clouds of points that, using an open source built-in feature, depict some trends that are not very telling. So we decided to implement custom calculations with Compound Discoverer. In order to do that, we need to make sure that we had RStudio and some libraries installed. This will allow us to extract the variables connected to the Kendrick mass defect. First, we will need a new blank script in order to specify the information we want to extract from the CD tables. the executable R script already installed at the map, and then we will include the full path of the script in the command line, making sure that the parameters are set true to get the zip file. You will find exported text and the JSON file, and then we will need to open the JSON file in Notepad++, where the scripting node will replace the expression arguments to the full path that is allocated in a temporary folder. It's the same as the JSON, and then we can do the math. The new columns will be written as JSON file updated. Have the chance to get the new columns in the CD results table. However, it may retrieve an error if the map is not correct, but eventually you can get them in spite of the warnings on existing columns, for instance. Then finally we'll get an integrated view in the compounds table. With the new columns, we can easily take apart the charge states, plot any of the variables using the colored third dimension, and the scattered cloud, originally with M over Z, will become interesting by plotting the molecular mass instead. Even more by using the ceiling rounding, we can see them jump up the plot. Also, we can get other metrics as well as cross-check with other variables like the retention time to easily select each feature. The built-in KMD plots, you can change different parts, the repeating units, and choose from the rounding options to resolve the features better. Having said that, we can get the feature selected of double charge clusters patterns on the volcano plot, and then filter them by DDA, for instance, with the corresponding ions. This is an example of the order findings classified in CD. You can see here the MS2 of each one. And when plotting the PCA for the study, you not only see them clustered afar from the bits, the salts, but filtering only by MS2, the DDA data only, we will get the same separation on the first component. That's very interesting because the same pattern is shown here in the heat maps. So we reduce the problem, and we are considering not to use the ceramic homogenizers at this stage. Therefore, we decided to include the width matrix to evaluate the solvent, acetonite, and water by using another design with only the salts bits and only the solvent as reference. So here we can see the differences by filtering. You can see here the M3, which is the only bits in a different position, and the PCA plots show the same behavior as well as the different clusters. So we have here the same situation. The same separation is only because of the compounds already pre-selected. In addition, we also realized that the compounds tend to bind the materials by comparing a post-extraction spike with a filtered extract. This led us to use a glass microfiber membrane. The compounds with higher molecular mass tend to get more absorbed in the surface. As we kept having low recoveries, we decided to evaluate the freeze-out step we use in the serial method version. When we take a look at the molecular level taking place by the strong dipolar moment of the acetonitrile, the ethoxylated alcohol's behavior can be described, but we won't get into the intricate details of the motions played by this Lejevin's equation. The take-home message is that the stochastic term also includes the time and temperature, which arguably leads to the formation of, for instance, micelles, which can be flocculating out of the bulk solution. When we drop the temperature until like -20, they are out of the solution, and it will affect our recoveries then. We tested the influence of these two last factors, the extract composition and the freeze out. And long story short, we need to go for the dilute and shoot in order to keep the ethoxylates in solution as shown in the box plot. So we need to avoid the freeze out step. Under such conditions, we moved on to the validation, where we have general recoveries by chain length and repeating units that are acceptable, and the QCs are in the accepted limits as well, with findings in some of the tested matrices. So 5 main takeaways from today's sessions. The Thermo Scientific Compound Discoverer software helped to identify the pesticide residues, but there's still concerns about this sensitivity, but it has to be with the instrument. The charge states show different slopes in customized KDM plots. The multiple charge is their preferred trace for quantitation of these cetyl ethoxylates. The visualization tools in CD help to unveil the source of this interference during the sample prep. The use of glassware materials is mandatory to avoid loss of these compounds by surface binding. The catcher's method using water and low water content matrices ensures acceptable recoveries, but avoiding freeze out, only dilute and shoot. So with this, we end this presentation, and thank you for your attention, and I will be taking a couple of questions later on.
Hello, my name is Ralf Tautenhahn. I'm the product manager of Compound Discoverer, and today I would like to talk about the new features in version 3.4 of our Compound Discoverer software. Here is an overview of the most important features in this new version of Compound Discoverer. Compound Discoverer can now be connected to Thermo Scientific's ARIA platform for direct raw data access and result file upload. It includes a new lipid search node for simplified lipid identification. There is a new node to perform QC for small molecule experiments using internal standards. Compound Discoverer now automatically detects and groups in-source fragments. It also connects to the latest version of our MC Cloud spectral library for improved compound identification. And there are several performance improvements which make the software up to 8 times faster. The first new feature I would like to talk about is the connection to ARIA. What is ARIA? The ARIA platform provides a solution for secure, centralized data management. Data acquired on Thermo Fisher Scientific instruments can be uploaded automatically onto the ARIA server. Data processing software like Compound Discoverer, Proteome Discoverer, or Biopharma Finder, for example, can then directly access the raw data that is stored on the server, process the data, and upload results back onto the server. The ARIA platform also provides capabilities for instrument management, user management, and it can be connected to third-party software like Skyline. So starting with version 3.4, Compound Discoverer software can now be connected to the ARIA platform for direct raw data access and result file upload. The benefits include that your raw files are stored in a secure central location. There is no need to manually transfer the raw files from the acquisition PC to the data processing PC. It helps to minimize the presence of multiple copies of the experimental data in various locations, and Compound Discoverer result files can be easily shared with other people in your lab. I should mention that the connection to ARIA is optional. Compound Discoverer can also still be used without an ARIA server. So how does it work if you want to use Compound Discoverer with an ARIA server? First, you have to register the software with your server. This only has to be done once. You would go into the configuration, click on server registration, click the register button. It will then ask you for the URL of your ARDIA server, and once you confirm that, you have to enter your credentials. After that, Compound Discoverer will be automatically connected to the ARDIA server whenever you run Compound Discoverer. When you then create a new study or add new files to a study, there will be two options. You can add files that are located on your PC, or you can choose the remote option. When you click on Remote Injections, this dialog pops up. It shows you files and folders that are located on your ARDIA server. You select the injections that you want to analyze. The supported file types for processing in Compound Discoverer are Excalibur RAW files, as well as Chromeleon CDS data files. You then confirm the selection by clicking Select in the bottom right corner, and this dialog will close. Compound Discoverer will now show the input files that you selected. The remote status column, as highlighted here, indicates that these files are located on the ARDIA server. The files will be downloaded automatically onto the data processing PC when the processing starts. If you want to follow this process, you can look at the job queue. Here you can see how your input files are downloaded automatically when the processing is started. It is important to know that these temporary copies of your raw files will be automatically deleted when the processing is finished. In a similar way, you can upload result files onto the ARDIA server. You simply select one or more result files and then you click the Publish button. A progress bar will pop up and show the upload process. Once the upload is complete, a check mark in the remote status column will indicate that a result file is now available on the ARDIA server and can be shared, for example. The next new feature I would like to talk about is lipid search in Compound Discoverer. Lipid search, which is made by MKI based in Japan, was previously only available as standalone software. Now, lipid search is integrated into Compound Discoverer and can be used as a node in your data processing workflow. Lipid search provides automated identification of lipids with a comprehensive database containing more than 1.5 million lipid ions and their predicted fragment ions. The lipid search node can be added to any untargeted data processing workflow, and there is also a new workflow template available specifically for lipidomics called Untargeted Lipidomics using lipid search. There are two things I wanted to mention in this context. Lipid search is also still available as a standalone software, as shown here, and the lipid search node in Compound Discoverer does not require the lipid search standalone software to be installed. The new lipid search node, as shown here in the workflow, is used in a very similar way like other nodes for identification purposes, for example SearchMZ Cloud, SearchMZ Vault, or predicting elemental composition. All these nodes are attached to the Assemble Compounds node. This node is also new in this version. I will talk about this in a few more minutes. When you select the lipid search node in the workflow, you see the different options that are available. At the top you have the usual parameters for mass tolerance and adduct ions to consider, and then, just like in the lipid search standalone software, you have all the different lipid classes and subclasses that you can select and that you want lipid search to take into account. Let's take a look at the result file. Typical result when using lipid search. In the name column you would have the lipid annotations coming from lipid search. Under annotation source you will see an additional annotation source here, lipid search, and then the consensus as usual. And when you click on one compound, one lipid, you will then have more details in the lipid search results subtable. Let me zoom in a bit on this result table. When you select a lipid here, you have all the additional details shown in the subtable, like lipid structure, name, lipid class and subclass name, rank, grade, and all the different scores as provided by Lipid Search. When you click on one of the Lipid Search results in the Lipid Search subtable, you will now see the MS2 spectrum for this compound, and in green you see highlighted those fragments that match Lipid Search's database, and on top of this you have annotations for each fragment as provided by Lipid Search. And just one more thing I would like to mention for Lipid Search. It is possible to bring additional metadata from the Lipid Search result back into the compounds table. So when you assign your priorities for the data sources in the Assign Compound Annotations node, you can select which metadata you want to bring back into the compounds table. It is possible to show the grade for lipids IDs in the compounds table, but you can also show the lipid class or the SMILE string, for example, in the compounds table. Moving on to the next new feature, quality control for small molecule experiments using internal standards. To calculate QC metrics, the software detects internal standards, stable isotope labeled or unlabeled, across all the samples. It then provides a report and different options to visualize things like mass error, retention time deviation, etc. This is now available as a new node in Compound Discoverer, and there's no longer a need to have separate software for this kind of quality control. To manage your internal standards in Compound Discoverer, there is a new menu called Internal Standards under Lists and Libraries. Here you can have multiple lists of internal standards, for example one for positive and one for negative mode. You can simply enter your internal standards here. For each standard, name and formula is required. Retention time is optional. If you do not provide retention time, the software will simply look for the biggest peak at the calculated mass. There are two ways how you can use the new Detect Internal Standards node. You can run a very simple and fast QC workflow using the workflow template provided under QC using internal standards. This workflow is very fast. In my experiment, it took less than 2 minutes for 50 samples. It is a simple targeted extraction of your internal standards, and you can use it to quickly check the data quality using your internal standards before analyzing the entire data set. And what you can also do is you can add the Detect Internal Standards node to your full processing workflow, for example metabolomics, and that way you also have the internal standards report available in your result file. This is what the result table for the detection of internal standards looks like. It's simply a table where you have one row for each standard, and if the standard was detected in a certain sample, then you have these values filled in, otherwise it will be grayed out. So for each standard in each file, it will report the mass error, retention time deviation, peak area, intensity, and also things like peak rating. You can then use the trend chart tool in Compound Discoverer to visualize these values. So here, for example, for these two selected standards, we can see the mass error plotted across 48 different samples. You can also choose to visualize other things, for example, retention time or peak rating or intensity, etc. Next, I would like to talk about the improved feature detection and component assembly. In version 3.4, we separated the feature detection from the component assembly. There's a new node called Detect Features. In combination with the Group Features node, this now creates a table of grouped features across all the samples, which is available in addition to the compounds table, which is created later in the workflow. This separation provides more flexibility in the processing workflow and also increased performance. There is a new node called Assemble Compounds. This node includes our new and improved component assembly algorithm, which is not only capable of grouping adducts and multimers, but now also in-source fragments. This new algorithm also utilizes the MZCloud spectral library in the component assembly process to determine adducts and in-source fragments. In previous versions of Compound Discoverer, we had the Detect Compounds node. This node has now been replaced by 3 different nodes: Detect Features, Group Features, and Assemble Compounds. Let's take a closer look at what each of these nodes are doing. The Detect Feature node performs untargeted feature detection in each file. The Group Features node then groups features across file, and it creates the features table. We'll look at this table in just a moment. And then the Assemble Compounds node first runs a preliminary MZCloud search. It then performs component assembly, meaning it groups all ions for each compound and also in-source fragments, taking into consideration the information that was retrieved from the MZCloud library. It then creates the compounds table. Shown here are the settings for the new Assemble Compounds node. You have mass tolerances up here. You can turn the MZCloud search that is performed on or off. You would turn it off, for example, if you don't have access to the internet. The in-source fragment annotation can be turned on or off. Under adduct detection here, these options are very similar compared to previous versions. You have the ions to consider and also the base ions to consider. This section is completely new. This is the optional MZCloud search, the initial MZCloud search that is performed as part of the component assembly process. So these settings are here. And then finally, under MS1 fragments detection, you have a setting where you can set the strategy to use for the in-source fragment detection and annotation. Since we are switching to this new feature-based workflow in version 3.4, there are a couple other changes that I would like to mention. First of all, the Fill Gaps node is now attached to the Group Features node. There is a new node called Assign Compound Areas. This node will attach the final peak area columns in the compounds table. In general, you will see that identification-related nodes and peak area-related nodes are now fully separated in this version. This gives us more flexibility for reprocessing. You can, for example, reprocess the Assemble Compounds node by itself without triggering reprocessing of Detect Features or Fill Gaps, for example. All the workflow templates have been updated to reflect this new format, and we would encourage you to use the new workflow templates in version 3.4. I mentioned earlier that in this version there is a new features table available. In previous versions of Compound Discoverer there was a features per file main table and of course also features per file related tables, but in this version there is now also a features main table. This table contains a list of all features, meaning M over Z at a certain retention time, grouped across all the samples. It also includes information about gap filling, peak weighting, peak area, intensity, MS2, and more. The compounds table, shown here, is very similar compared to previous versions. But what is new is that you can now open the features table directly as a related table. So shown here, for example, is highlighting the first compound in the compounds table, and I'm now opening the features table as a related table. In the features table as a related table, you now see all the ions that were grouped together for this compound. This is polarity switching mode data, so you see both ions from positive as well as negative mode grouped together here. New in version 3.4, you now also see in-source fragments that were detected. So these fragments are also now grouped as features for this compound. In this example, citric acid. There are a couple new columns in the compounds table that I would like to explain briefly. There is a new column called polarity. This column indicates if a compound was detected in positive or negative ionization mode or both. There is a new column called comments. This column is editable and you can use it to leave comments. A very interesting new column is called MS2 purity. This column reflects the precursor isolation purity for the MS2 data. It is calculated by dividing the intensity of the targeted mass centroid by the total intensity of all centroids within the isolation window. If this value is much lower than 100%, that means there were also other centroids within the isolation window besides the precursor that was targeted, resulting possibly in a chimeric spectrum. I'm switching gears and I would like to talk about performance improvements in Compound Discover 3.4. The dataset that I used for benchmarking is based on soy source. It has 115 samples including replicates, and it was measured on a Q-exactive HF. The PC that I used is a Dell P7920 workstation, which is already a couple years old. This table gives you an overview of the performance improvements for the last 2 releases of Compound Discoverer. We are looking at the runtime for 4 selected nodes: alignment, detect compounds, fill gaps, and MZLogic, as well as the total runtime. So using version 3.3 SP2 as a baseline, we see alignment took 40 minutes, detect compounds 4 hours, fill gaps 16 hours, MZLogic almost 15 hours, resulting in a total runtime of 38 hours. In version SP3 we saw major performance improvements. You see that especially gap filling and MZLogic is much faster, resulting in a total runtime of 13 hours. And then we also see the difference here when the result file is located on a solid state drive compared to a hard drive, again reducing the overall runtime down to 10 hours. And then we see an additional boost in performance in version 3.4, where now again the runtime for feature detection and component assembly is reduced, gap filling is reduced again, and MZLogic is faster, and now the total runtime is only 4 hours and 20 minutes. Another area that has been improved in Compound Discover 3.4 is compound identification. Compound Discoverer now connects to the new and improved version 2.0 of the MZCloud Spectral Library. In this version, MZCloud contains more than 16.5 million spectra, 32,000 MS entries, almost 8 million spectra were added in the latest upload. There was also a significant addition of therapeutic drugs and endogenous metabolites, complete with MSN data. A lot of PFAS standards have been added recently, and one major improvement is that more metadata like compound classes, Cas numbers, and HMDB IDs are available and can be displayed in Compound Discoverer. When I talked about lipid search earlier, I mentioned that additional metadata from a lipid search result can be pushed and displayed in the compounds table. This is very similar with MZCloud. So when you define and prioritize your data sources in the Assign Compound Annotations node, under MZCloud Search, you have a menu where you can select additional metadata. For example, here I selected compound class, CAC ID, Cas number, HMDB, and INCHI key. There's more available, for example, also SMILE string, INCHI, PubChem ID, etc. And then in the result, like shown here, you will see for all those compounds that have been identified using MZCloud, you see these additional columns displayed: compound class, CAC ID, Cas number, HMDB ID, as well as INCHI key. For customers that cannot use the live version of MZCloud, there is a snapshot available, which we call the MZCloud Offline Spectral Library. This new snapshot, the 2024 version, ships with Compound Discoverer 3.4. It contains the entire reference and order process libraries, as well as application-specific subsets, for example, endogenous metabolites, PFAS, pesticides, and herbicides, sports doping agents, etc. We also made some improvements in the way spectral libraries and mass lists are used in Compound Discoverer. In previous versions, there was only one set of parameters that would be applied to different libraries or databases. Now the software supports the use of different sets of parameters for different spectral libraries or mass lists. So that way you could, for example, use very strict settings for the MZCloud offline library. You could use some very liberal settings when using in silico libraries, and you could enable retention time match for custom libraries. That allows you to match more precisely when multiple libraries or mass lists are used, especially with different quality, and that way you can also define priorities. To explain the next new feature, which is related to fish scoring and MZLogic, I'd like to back up a little bit and explain how these tools are used. So even with comprehensive spectral libraries like MZCloud or the NIST MSMS library, unfortunately we still often end up in a situation where we don't get any hits from the spectral library, but instead we have to rely on hits that we're getting from a structural database like ChemSpider, shown here. There are two different methods available in Compound Discoverer that use the fragmentation data to calculate a score, which can then be used to rank order these structure proposals and find the best candidates. The first method is MZLogic. MZLogic looks for compounds with similar fragmentation spectra on MZCloud. It calculates the structural overlap between those hits and the structure proposals. It combines the score from the structural overlap and the spectral similarity into a final score. This method is very fast. It uses actual fragmentation data from a curated spectral library, MZCloud. The second method is called fish scoring. Fish scoring is based on in silico fragmentation using Mass Frontier software with 52,000 fragmentation schemes from peer-reviewed literature. This method is computationally more intensive. The result is a structurally annotated fragmentation spectrum with the score, basically the number of fragments that can be explained versus all the fragments in the spectrum. In both cases, you end up with a score for each of those structure proposals, which can then be used to rank order these putative structures and find the best candidates. The improvement that I would like to talk about now is that there is more flexibility in calculating MZLogic and fish scores in this new version of Compound Discoverer. In previous versions, when using the imply MZLogic node, it would automatically calculate the MZLogic score for all compounds. However, the MZLogic score might not necessarily be needed for all compounds. So in version 3.4, there is now an option to compute the MZLogic score for all or only for selected compounds, which can really save time, especially in those cases when you only need the score for a couple selected compounds. And it is sort of the other way around for fish scoring. In previous versions, Compound Discoverer would only allow to apply the fish scoring manually on selected structure proposals, which can be quite tedious if many structures need to be selected. Now we are introducing a new node, the apply fish scoring node, which automatically calculates the fish score for all structure proposals of all selected compounds, which really is a convenient way to calculate fish score for all compounds of interest. How does it work, scoring all compounds versus selected compounds? I would like to explain this using the apply fish scoring node as an example. Here, the apply fish scoring node was added to the initial workflow, meaning we are in full processing mode, and the apply fish scoring node will automatically calculate the fish score for all compounds, which can be potentially quite slow. However, if you first process your workflow without the apply fish scoring node, then select compounds that you're interested in, click on partial reprocessing, then now all these nodes that have already been processed are grayed out, and only the apply fish scoring node in this example will be processed, which means it will calculate the fish score only for those compounds that have been selected, which is much faster. I would like to explain this one more time, but now looking at the result file. So the way this works is that you would first run your initial analysis without the fish scoring node and open the result file. Now you would select the compounds to be processed by checking them in this column. You now close the result, select partial reprocessing, add the fish scoring node to the workflow and click Run. After the workflow has been completed, the fish score is now available for all ChemSpider, MassList results, and other databases and can be used to rank candidate structures. In a very similar way, like I mentioned earlier, the Apply Emsologic node can be used to only calculate Emsologic score for selected compounds, and the same mechanism also works for the Generate Molecular Networks node, which is really important if you would like to analyze very large data sets with thousands of compounds. If you then only select a subset, then the processing for these nodes can be much faster. Switching gears again, I would like to talk about an update in a different area. Compound Discoverer has the capability to generate molecular networks, and in this new version of Compound Discoverer, we have added the capability to inject a seed compound into a molecular network. A seed compound is a compound of interest that is not present in the dataset, but when added to the network, it can form clusters by connecting related compounds and that way help with the interpretation of the network. In this example shown here, we have added several fragments that are characteristic for PFAS compounds as a seed compound shown here. And now you can see that different PFAS related compounds are connected, are forming clusters and are connected to this artificial seed. Compound Discoverer comes with several databases that are pre-installed, but there are also additional databases available for download. We have recently added these two to our website. One is the DSS Tox database and the other one is the PubChem Lite database. These two databases are available for Compound Discoverer and can be downloaded on the website as shown at the very bottom of the screen. There are also some updates for GCMS workflows. We have added a new column to the GCEI compounds table and the GCEI compounds profile table, and that is the area all ions column, which has been frequently requested by our customers. The Calculate Mass Defect node and the Mass Defect view are now also available for GCCI data. There's a new PFAS compound database and a new PFAS workflow template available. On my last slide for today, I would like to highlight resources that are available. There is our support email address, cd.support@thermofisher.com, the product website with a lot of information around Compound Discoverer. Then we have the mycompounddiscoverer.com website, which contains a lot of material around scripting notes, news and updates. There's a way to request features and a help button. Then we have our documentation portal. It contains all the manuals as well as tutorials. There was a webinar recently on scripting notes for Compound Discoverer. The recording is still available here, and we also have recordings available from last year's online training. These recordings, as well as a copy of this slide deck, can be requested from our support email address. Thank you for your attention.
All right. Thank you both very much for those very informative presentations. At this time, we're going to start with the live Q&A. We did receive a number of questions, so we'll try to work through the best we can here. Let's see here. Julio, we'll start with you. How does the sensitivity achieved by your method compare to the current sensitivity of the LC-HRMS?
Well, we are currently injecting 2 microliters to achieve sensitivity in samples in a mass fraction about 10 micrograms per kilogram, which is the standard MRL. But now the modern systems like just triple quads, the ultimate sensitivity, they can reach the same sensitivity with only 0.5 microliters. If we can inject more, we can reach that sensitivity, but it's about there's like different technologies. So it's good enough for our purposes, but for sure the triples are more sensitive.
All right, thank you. Ralf, can Compound Discover 3.4 and the previous version 3.3 be installed on the same PC?
Yes, absolutely. You can install CD 3.4 in parallel with the previous version or any previous version. You cannot run them at the same time, but you can certainly install them on the same PC.
All right. Julio, in case of Acrorex Deep Scan, how many iterations were performed and why?
Well, in average, we reach like the whole MS2 universe in around like 3 to 5 iterations. So I would say that it depends on the complexity of the matrix. We were working with serials, and as long as you can have all like the iterations without any MS2 scans, it's probably 5 a good number.
All right. Another one for you. Why is sensitivity important for the residues with MLR complex definitions?
It is very important. It's critical because in case of, let's say, an isomer that is included in the complex residue definition, you have to go halfway. You need to go lower, yes, because they will be both included in the same complex residue definition. So you will need to go to half the value of the emerald. And in cases of multiple metabolites, it has to be low, even lower, yes. So it is critical. We need to work in that. So that's the challenge here as well.
All right. Ralf, does the lipid search function available in CD 3.4 require the lipid search software?
It does not. You can simply install Compound Discover 3.4 without having lipid search installed. It does not require the lipid search software or a separate lipid search license.
All right. Another one for you. How could we scan and select identical or diagnostic fragments among all the compounds in Compound Discover?
That is possible. There is a function in CD 3.4 and also in CD 3.3. We call it compound class scoring. So there is a node that does that. You can define fragments, one or more fragments to look for, and then Compound Discoverer will go through all the compounds. It will look at the fragmentation data, and if one or more of those fragments are found, then it will calculate a score, and the score will be higher the more fragments are found and the higher the intensity of those fragments.
Right. Julio, must the freezing out be avoided for all matrices, or was it only for wheat?
Well, the freezing out step is standard for the catcher's method when you're dealing with cereals and low water content matrices that probably had like a lipid fraction, so it's like a cleanup step. So in that case, you need to avoid it. Otherwise, you will get rid of the compounds because it has to be with the compounds. For fruits and vegetables and other matrices, it's not standard, so it doesn't affect.
Okay. Ralf, what is the difference between using the internal standard node and using the masked list search node with internal standards?
That's a great question. So these two work in very different ways. When you're searching a mass list, then this will basically work on top of the untargeted detection, right? You get your compounds table, and then searching a mass list will provide an additional layer of information for this compounds table. The detect internal standards node works very differently. It will do a targeted detection only for those internal standards. So there were a couple advantages here. First of all, it's super fast. It will really just do a targeted detection for those internal standards. And the second advantage is that very often you would use labeled internal standards, right? And in the untargeted workflow, sometimes labeled compounds, especially fully labeled compounds, are not detected because they don't have a regular isotopic pattern, which is required with the default settings. So yeah, with the detect internal standards, even labeled standards can be detected really easily and automatically.
All right. Another one here for you. Do you need to use MZ Cloud for the source fragment search?
Also a good question. That is actually optional. So there were a couple options that you can choose in the component assembly node. Per default, it will try to use the online version of MZ Cloud, but it's also possible to basically only use the fragments from the MS2 data. It will try to look for fragments that are present in the fragmentation data, and if at the same time we also see these peaks in the full scan, right, then it will detect those as in-source fragments. If a connection to MZ Cloud is available, then it can use MZ Cloud as an additional step to validate this information. Since on MZ Cloud we have low collision energy information available for pretty much all these standards that are on MZ Cloud. So we can use the low collision energy information that is available there as a step to confirm that this really is an in-source fragment, right? And avoid false positives. So it's an optional step. In our experience, the specificity is better if MZ Cloud can be used, but it is absolutely possible to also annotate in-source fragments without using MZ Cloud.
All right, got time for a few more here. Julio, why did you create additional variables for coformulants from the same data when KM plots are already available?
That's also a great question because it's by default there's like a Kendrick mass defect graph plots over there, but the thing is that the Kendrick mass defect is also a function of charge. So in order to take it apart, I needed to recalculate and have the charge in a separate column. Yeah. So at the end, I end up with the different variables, and then I can make these calculations, and you can plot them in an independent way. Yeah. So in that case, you can tell the charge of the different types of coformulants and understand and for instance, use the colored function, 3D color function, to make them visible and easily to understand.
All right, and one more for you. Why were the mentioned M3 extraction samples positioned on different axes in the PCA if both sample clusters were produced with beads?
Yes, it's true. Both samples are positioned in different parts. What they have in common is that they included like these coformulants, so they were separated by both principal components in 1 and 2, but they are different because they are one from the solvent and the other one from the matrix. So they are not clustered together, but in different axes.
All right, Ralf, we've got another one here. Are there any changes to the scripting node in 3.4 to go along with the new tables added?
Mm-hmm. There are no changes in the scripting node itself. So the scripting node works the same way as in version CD3.3. But if you have written a scripting node, then you might have to adjust some of the names. So for example, I mentioned some of the new columns in Compound Discover 3.4. So if you want to make use of these new columns, that would be possible. And there were maybe one or two places I can think of where column names or table names have changed a little bit. So that's maybe you would have to adjust for that. And I see a related question here. People are asking how is it possible to rewatch the scripting node webinar? I would recommend to go to mycompounddiscoverer.com. There we have all the material on how to create a scripting node, and there's also a link to the recording.
All right, excellent. So we've got time for one more. So in Compound Discover 3.4, for the in-source fragments shown in the related table, does it mean that they will not show as candidate compound in the main table?
That's correct. That's absolutely the way it works. So Compound Discoverer will automatically group these in-source fragments with the compounds. So they don't show up as a separate compound in the compounds table. That's exactly the way it's supposed to work. You can see those fragments when you go to the features subtable in CETA 3.4. It's called the features subtable or related table. This is where you will see all adducts, fragments, cluster ions, and now also those in-source fragments grouped together with the precursor.
All right, thank you both very much for your great presentations and for your time today and your important research. We'd like to thank LabRoots and our sponsor, Thermo Fisher Scientific, for underwriting today's educational webcast. I'd also like to thank the audience for joining us and all the questions. Questions we didn't have time for today, and those that get submitted during On Demand will be submitted to our speakers. This webcast can be viewed on demand, like I mentioned. LabRoots will alert you via email when it's available for replay, and we do encourage you to share that email with your colleagues who may have missed today's live event. So until next time, thank you very much and goodbye.